All right, we're now going to start looking at slightly more complicated circuits, and by that I just mean ones that involve more than a single resistor connected to a single battery. And so our first goal with these is really just to develop some rules about how voltage and current works in these circuits, and that's going to help us to analyze what's happening with these circuits. So we'll start with voltage, and then we'll move into rules about current. So our rule here with voltage is that in every loop, every possible pathway through the circuit, the sum of the voltages, more properly known as potential differences, equals the voltage of the power supply or battery, whatever it is that's providing power to the circuit. Okay, so no matter what loop we take, and if we think about this circuit here, here's our battery, we could take this pathway, we could take this pathway, we could take this pathway. No matter what pathway we take, the voltage across that pathway must add up to the voltage of the circuit. And we see that. So if we take this red loop, we have 10 volts across that single resistor. That equals the voltage of the battery, which is 10 volts. If we take this blue loop, we have 5 volts plus 2 volts is 7, plus 3 volts gives us 10, which is the voltage of the battery. And if we take that outer loop, we have 5 volts plus 2 volts plus 3 volts. That once again adds up to 10. Okay. The other thing that's really important to note is that when the circuit splits and then comes back together, like it does here, it splits at this point and then comes back together here, the voltages across each pathway must be the same, and we see that they are. Both of them have 2 volts of voltage across them. One way that I help to understand this is I create this analogy where we think of voltage like height, and I think about batteries as elevators that basically lift the electrons up to some height. And so we're going to take a look at that analogy and how that helps to explain this idea of voltage. So thinking about this elevator analogy here, I think about the battery as something that brings the electrons up to some height, all right, like an elevator that lifts objects up to the top of a mountain, which I know really isn't a thing, but just go with it. And then once the electrons are up there, they have all these different pathways that they can take to get down the mountain, and some of them split and come back together, all right? But there's all these different pathways that the electrons can take to get back down the mountain. But what we know for sure is no matter what, all right, in order to get back down to the start of the elevator, we have to lose whatever height we gained going up the elevator. So if we gained 10 meters of height in order to get back down, we have to lose 10 meters of height no matter what path we take to get back down there. That's what voltage really is. The other thing we see that works with this analogy is right here is a split in the circuit like we saw in our diagram on the last page. And when that circuit splits, you can either go this way or you can go this way, but then the circuit comes back together. And much like a path going down a mountain, if the path split and then came back together, your drop in height for the one path and your drop in height for the other must be the same because those paths eventually meet back up and come back together. So that's what voltage is like. So let's go ahead and try a practice problem here. So I'm going to create some loops through this circuit here and use this idea that the voltage must add up to the voltage of the battery, which in this case is 30 volts. And we're going to fill in some of these missing voltages. So I'm going to start with a loop that goes all the way around the outside. And I'm going to go in a clockwise direction, but if you did counterclockwise, that would work as well. And so what we're going to have here is we hit 17 volts plus we hit a 4 volt resistor, plus we hit a blank resistor, which I'll just call X. So there's 17, 4, and then X. And that must add up to 30. So in order for that to be true, we must have 9 volts across this resistor. Right? 17 plus 4 plus 9 gives us 30. I'm then going to take a middle loop here. So I'm going to take this loop there. Okay. And same basic idea here. I hit a 6 volt resistor, then I hit a blank one right here, then I hit a 4 volt resistor plus a 9 volt, and that needs to add up to 30. Okay, and so when I solve for that X there, I end up getting that is going to be 11 volts. All right, because 6 plus 11 plus 4 plus 9 gives me 30. So this is going to be 11 volts here. right? And then finally I take this inner loop here, and I see I have X, some unknown resistor here, plus 11, plus 4, plus 9, and that needs to add up to 30 once again. And when I solve for that X, I get that this is going to be 6 volts. Now, it is a coincidence that both of these happen to be 6 and both of these happen to be 11, but what's not a coincidence is that this branch as a whole here is 17 volts. This branch as a whole is 17 volts, and this branch with that single resistor is also 17 volts, because we see the circuit splits here, and you can take one of 3 pathways and it all comes back together here. So we know that all 3 of those pathways must lose 17 volts, the same amount, in order to be able to come back together. All right, for this next one, before I start doing my loops, I'm first going to just see right here that I have 2 resistors that are in parallel. I know the circuit splits here, and then it comes back together here, and so that means both of these must have the same voltage across them, so I'm just going to fill that in as 8 volts. We certainly could have done that through our loops, but that saves us a little step here. So what I'm going to do then is I'm going to start thinking about my different pathways. So I have this one possible green pathway here, going around, and using that pathway I see that I'm going to have 8 plus 6 plus a blank resistor here. That needs to add up to 15, so that means that this one here is going to be 1 volt. Okay. I next can take this blue pathway here around, and I don't need to worry about that other pathway through the other 8. That doesn't really matter because it's really the same whether I go this way or this way. So I'm not bothering that, but that would be a possible pathway. So thinking about this blue pathway, we have a 2, a blank, a 6, and then a 1. So that means this one here, in order to add up to 15, must be 6 volts. Okay, and then for my final pathway, I'm going to go all the way around to the outside, looking like that. I realize again that I am skipping that one resistor, but once I know this one, I'll also know this one. So thinking about this red pathway here, I have a 3, a blank, a 6, and then a 1. So that means this blank here must be 5 volts, and if this one is 5 volts, that means that this one here must also be 5 volts, because again, my circuit splits at this point. You go one way or the other and comes back together, so both of these must have the same voltage. All right, we're going to continue on now and jump over to current. And so the rule for current is a little bit different than voltage. The rule for current is that the total current going into a junction must equal the total current leaving the junction. All right, and so what we're really thinking about is when the circuit splits, we're thinking about how much current we have running through that wire before the split, and then how much current we have leaving that wire after the junction, after the split. It also means that when you have 2 resistors that are one after another, okay, the current must be the same through both of those resistors. So this is a little bit like the rule we had for voltage. When it splits and comes back together, the voltage across those had to be the same. With current, it's when you have one right after another, the current has to be the same. All right, and really the way I understand this is through the flow of traffic. Okay, and so let's take a look at this example circuit here to try and apply these rules. So what I'm thinking about is some amount of current, it tells me 25 amps, is leaving this battery here. It comes up to this junction here, and I see that 10 amps goes that way to ultimately flow through this resistor, and the remaining 15 amps goes this way to ultimately flow through this resistor. Okay, so there's my first split. That 10 amps then comes around to this split here, and I see that 3 amps goes and takes the branch on the right, and the remaining 7 amps takes the branch on the left. So we see that 10 splits into 3 and 7. It then comes back together here at this junction. The 3 and the 7 come back together to form 10 amps once again. And then lastly, that 10 amps is going to join up with the 15 amps that was flowing around this branch here. So those 15 amps and these 10 amps come back together to create 25 amps returning to the battery. So that's the junction rule, right? We're thinking about each one of these junctions, each place where the circuit splits or where the circuit comes back together, and knowing that whatever current goes in is the current that leaves. And the analogy I use for this is thinking about traffic. Okay, current really is a measure of the flow of electrons, the flow of traffic. And it works very similarly to that, okay? Just like an intersection, whatever traffic goes into an intersection in a given amount of time must equal the traffic that leaves the intersection in a given amount of time. Sure, cars have a choice of going straight or right or left, but ultimately cars don't disappear in intersections. It's not the Bermuda Triangle. So traffic's a really useful analogy. We're going to take a look again at our idea of electrons coming down pathways on a mountain to use this traffic analogy. So here we have our mountain once again, and instead of thinking about all the different paths, we're going to just focus on junctions, okay? And so we see here, we start with 25 people. That represents our electrons at the top of the mountain, all right? We see that 15 go one way, 10 go the other way. So there's that idea of however many we start with, 25 must equal how many leave that initial split, that initial junction. We see another split right here, 10 go into that, and that splits into 7 and 3. The amount going in equals the amount leaving, but then they come back together, okay? And that 7 and that 3 recombine to form 10 through this pathway here, and that ultimately joins up here with the 15 coming down the other side, okay, to once again form 25. So you see, we don't lose electrons, we don't lose people, we don't lose current when we go into junctions. Whatever goes in is going to be how much leaves. All right, so once again, we have one of these blank circuits, and we want to fill in the missing currents now. So we're going to be thinking about junctions. We're also going to be looking for cases with current where there's one right after another, because those are going to be cases where we know the current has to be the same through both. So I actually see 3 to start out here. So we have 11 amps flowing through this resistor. That's going to continue on to that next resistor, so this one is 11. Down this branch, we have 3 going through this resistor, which means 3 must have first gone through that resistor because they're one right after another. And then going down this branch, we have 5 that starts. That 5 must continue on down, so that means that this is also 5 amps. Now let's analyze our junction sum. So this 11 amps of current comes up through the battery, and so we have 11 amps going into this junction right here. We know that 3 amps goes down, which means the remaining 8 amps will go straight. We then come up to this next junction that has 8 amps going in. We know that 5 amps will go down. The remaining current must go straight, so that's going to be 3 amps. That's our remaining current, which means that 3 will continue on around through this resistor. We can then recombine them. Obviously, we filled all of them in, but this will help really hammer home this idea of current going into junctions equals current leaving. So the 3 amps coming from this branch will combine with the 5 amps coming from this branch to form 8 amps here. That 8 amps will continue on to this next junction and combine with the 3 amps going down to ultimately form 11 amps going in and out of this junction. And so we can see how analyzing these junctions allows us to figure out how much current goes through these different resistors. We have one more here, and so we'll start with filling in ones where it's a continuation. So we do have one right off the bat here. 1.2 amps goes through this resistor, so it will continue through that next one. So this one is also 1.2 amps, right? Those are 2 resistors that are one right after another. I'm then going to turn to this junction here. We see that 0.9 amps came into that junction. It's going to split. 0.3 amps takes the pathway on the left, which means the remaining 0.6 amps will take the pathway on the right. That will then eventually recombine to be 0.9 amps when those 2 branches come back together. That 0.9, if we're thinking about this junction here, will combine with the 1.2 amps coming down. Okay, and that's going to form 2.1 amps going across that branch there. We look at this next junction here, and we see that we have 2.1 amps coming in from there. And if we think about this junction, that 2.5 and that 1 will come together to form a current here of 3.5 amps going down. Okay, those two will come together, and that ultimately meets up in this junction here to become 5.6 amps. That's what goes through this resistor here. That's what continues through this resistor here, okay, and then goes back around before eventually splitting up. And so there we have it. Again, we're really focused on junctions here with current and thinking about how much current goes in and how much leaves. These problems are kind of going to be like puzzles a little bit. You kind of just have to find what numbers you can find right off the bat. And it might be that, you know, in order to ultimately get these two, you had to find this one first and this one. All right. That's often going to be the case, that you might there's no like set order you have to work in. Just find what you can find and kind of keep looking for new currents or voltages that you can find based off of what you know.